Hi, in this video we'll be looking at how to understand the symmetry with respect to the x, y and the origin. Actually, in the past videos we've actually talked about how to test for the symmetry of an equation with respect to the x-axis, the y-axis and the origin. But I've decided to just create a new video just to ground understanding of the topic, that is, understanding the symmetry with respect to the x, the y and the origin. So probably by the time you watch these few videos, actually gives a pictorial representation of the whole synopsis, then you would have a clearer picture of what I discussed in the last video. Now what we are told to do here is to draw a complete graph so that it has the type of symmetry indicated. So we're told that assuming this graph here is symmetric with respect to the x-axis, assuming it is symmetric with respect to the x-axis, then we are told to complete the graph. Now there are two ways to look at this. Now whenever a graph is symmetric with respect to the x-axis, then for any point xy on the graph, then that graph must also contain point x negative y. That's what it means. Another way to look at this is that whenever a graph is symmetric with respect to the y-axis, it simply implies, with respect to the x-axis, it simply implies that the x-axis acts like a mirror. So that means for any point you have on the other side, we'll surely have an image at the other side of the mirror. So let's start by looking at this. Now according to this definition, what it says is that since we have point 02 here, now since we have that point, then it simply implies that 0, negative 2 must surely be there too. 0, negative 2. So you can see 2 becomes negative 2. And then another way to look at the whole picture, what I've just discussed right now, is since you have 0, 2 here, and then since this acts like a mirror, then the image of this is going to be this point here. So this point here, which is 0, negative 2. So similarly, since we have 5, 3, the image of 5, 3 is going to be 5, negative 3. According to this definition, we have 5, 3. So we should also have 5, negative 3. So this is 5, while this is negative 3 here, and when we draw it, we have this point here. That's 5, negative 3. And then it says we should complete the graph. So just join the point. And then we have a graph. So you could see it's symmetric with respect to the x-axis. So let's look at another question here. So here we're told that the graph here, we are assuming that the graph is symmetric with respect to the origin. And then we are told to complete this graph, if so. Now, what you need to note also here is that whenever a graph is symmetric with respect to the origin, the definition says that whenever there is any point xy on the graph, so you have a point xy on the graph, then that graph must also contain point negative x and negative y. So for each of the coordinates, it must also contain the negation of each of the coordinates. So an example, we have pi 2, that's pi all over 2, comma 2 on the graph. So according to this definition, it must contain negative pi over 2 and negative 2. So similarly, since we have pi 0, we have pi 0, then it must also contain negative pi and 0. That's what it means. So that's exactly what we have here. And then let's see how we can do that. So we have pi over 2, 2. We have pi over 2, 2. Negative pi over 2, 2. So this is negative pi over 2. It's somewhere here. This is going to be negative pi all over 2, 2. And the next one is we have pi over 0. So we should have negative pi all over 0. So that's somewhere around here. this is negative pi 0. So for this to be symmetric, we join this line here. So my graph is not cute, but you have a picture of exactly what I'm trying to talk about. Alright, let's go to another example here, which is the last case. Is we are assuming this graph here is symmetric with respect to the y-axis. So similarly, there are two ways you can look at this. Now, by definition, whenever you say a graph is symmetric with respect to the y-axis, it simply implies that for any point xy on the graph, then that graph must also contain negative x comma y. That is what it means. So for example, this graph here contains 0, 4. It contains 0, 4. So it must contain negative 0, which is the same thing as 0, but the 4 still stays. You can see the 4 still stays the way it is. So another point is 0, 0, which is also 0, 0, and then 2, 2. So 2, 2. Then it must contain the negation of the x coordinate only. That is negative 2 and 2 here. So you have this. So this stays, but the only one that changes is this man here. So we have negative 2, which is negative 2 here. This is our negative 2, and this is our 2. And when we project that, it should be somewhere around here. So this is negative 2, 2. And then we join the graph. So this is a graph assuming it is symmetric with respect to the y-axis. And then another way by which you could look at this is that whenever you say something is symmetric with respect to the y-axis, it simply implies that you're going to treat the y-axis. What's wrong with my line? You treat the y-axis as though it were a mirror. That's what you do. So you treat the y-axis as though it were a mirror. So if you're treating that, any point you have at the other side of the mirror should surely have an image at the other side of the mirror. And then since this is the only point at the other side of the mirror, this is going to be the image. And then all these points, all of them like this, they all have images. These are the images here. And then you have your nice graph. I do hope that with all these few examples we have done so far, probably it has given you a clear picture of what symmetry about the x-axis, about the y-axis, and about the origin, what it means. Thank you.